Okay. And of course, generators are generating EMF, electrical energy. So how? By three ways. In fact, the basic idea was changing the magnetic flux. A current can be induced in a circle by changing the magnetic field strength B, by moving the circular loop in or out of a magnetic field area, by changing the orientation of the loop with respect to magnetic field theta, AB cosine theta. So by these three ways, we can induce an EMF in a coil, which is in a coil. So which one is the more practical way? Third one. That's why third one is the method of generators. Yani changing the orientation of the loop with respect to magnetic field. Yani rotating a coil inside a magnetic field. So it is indicated in your book as a practical way of generating electrical energy. So devices and mechanical energy are called generators. Why mechanical energy converted to electrical energy? Because you are rotating it. You are rotating the coil inside a magnetic field. So rotational kinetic energy, it's a kind of mechanical energy. So this rotational kinetic energy is converted to, you get EMF, you get electric current to electrical energy. So generators convert mechanical energy to electrical energy. Simple definition, but mystery exam question. And this rotational kinetic energy provided by two ways. One of them is hydroelectric plants are used to rotate the coil inside generator. So this is the symbol, this is the generator here. This figure is representing generator. And this is the dam. You cut the water and then increase the potential energy because water rises when you cut the river. So this rising water accumulates potential energy. When you open a gate, so this gate allows water to flow down. So of course, when they are flowing down, this potential energy is converted to kinetic energy of the water flow. And we use a turbine here. You put the turbine on the way of water because this water must hit the blades of the turbine and turbine must start rotating. After that, this turbine is attached to the generator's coil. As turbine is rotating, generator's coil are also rotating inside a magnetic field. So then you induce an EMF in this generator, and this EMF is sent to the cities as electrical energy. So this is the first one. Using a hydroelectric plant, falling water directed against the blades of the turbine. So then this falling water hits the blades and then produce a torque about this axis of rotation, and turbine starts to rotate. This rotating turbine is attached to generator's coil. Coils are starting to rotate inside a magnetic field, and then they induce a current or EMF. This is the first one. Second one is coal or natural gas burning plants. So here we are going to use again water, but not river water. We are going to use some water, but we will heat that water. So coal or is burned in the furnaces. We are going to heat the coal, or we are going to heat the natural gas, and we will heat the water. This heated water will be converted to steam. Steam is, of course, moving with very high speed, and these steams are directed against a turbine again, but this turbine is steam turbine. It's a little different than that one. So when steam is flowing through this cylindric tube, so then there are some turbines, as you see, 1, 2, 3 is shown, and these turbines are starting to rotate like windmill in the wind. When you hold it across the wind causes an object to rotate. So steam is a kind of wind. It also causes these turbines to rotate. After that, this turbine's rotation is transferred to the generator. So generator's coil are rotating. As generator's coil are rotating, so then electricity is produced and then energy is sent to the city. So these are two basic methods of producing electrical energy. So rotational kinetic energy of the turbine is rotating the coils of the generator, and then when generator's coils are rotating, so they induce an EMF and then send to the city. Tur Turbine's rotational motion or rotary motion is transferred to the coils of the generator. So coil starts rotating with the turbine together in a magnetic field. As coil rotates with constant rotational speed, the angle between the normal of the coil and the magnetic field regularly changes. We are changing the orientation of the loop with respect to magnetic field. Yani we are changing the angle. So by angular speed, so then we induce an EMF by this generator. This steady change in angle, because it's continuously rotating, so angle is continuously steadily changes. This steady, constant change in an angle causes a change in magnetic flux and induces an EMF in the coil. This EMF equation is Banu sine omega t. This induced EMF equation can be obtained by using derivation, but I'm not going to prove it. So this induced EMF generator is a sine function. B, A, and omega. This is the maximum value of induced EMF multiplied by sine omega t. Yani induced EMF of a generator will be a sinusoidal graph like this one. So induced EMF will change according to time as time passes. So it's a sine graph, as you say. And maximum value is this. Maximum value of this induced EMF, negative or positive, will be calculated by B, A, and omega. Banu will say us how much is the maximum value of this induced EMF. This equation describes that sinusoidal variation of the EMF with time. E changes as a sine function. Yes, as time passes, E is changing as a sine function. This is a graph of the sine function. As I said, maximum value of induced EMF is boundary, positive Emax and negative Emax. So then this EMF is changing between these two maximum values. Magnitude of the induced EMF continuously changes. Yes, zero increases, much increases, and the maximum decreases, zero. Again increases in magnitude, but in opposite direction. Maximum decreases and then zero. So magnitude of the induced EMF continuously changes. And direction of induced current also, or induced EMF also changes. Positive, negative, positive, negative, positive, negative, and so on. This change in current or this change in EMF is called alternating current or alternating EMF and represented by AC. And in 1 second, this one full cycle of this alternating induced current undergoes one full cycle. This is called one full cycle. One pulse up, one pulse down. It is one full cycle. This alternating current undergoes one full cycle of change in direction 50 times each second. Yani there will be 50 cycles in 1 second. This is defining the frequency of this alternating EMF and represented by F is equal to 50 Hertz. And as I said, maximum value of induced EMF is calculated by positive BAN omega, yani Banu. But instantaneous values continuously changing. So here is zero, here is increasing, and then gets maximum, decreases, and zero, increase, and then maximum, decreases, and zero. So instantaneous values continuously changing. This means exam question. They are asking you, which are the following value of an alternating current changes? Instantaneous values changing because it depends on instant, it depends on time. But maximum value is constant, it's Banu. B and omega, it depends on B, it depends on A, it depends on N and omega. So when for a generator, this value does not change. But as time passes, instantaneous values continuously changing. This omega is known as angular speed. Remember, we know in the chapter 1, section 1. But in the this section also sometimes it's called rotational speed, or sometimes it's called angular frequency. Angular frequency, angular speed, and then rotational speed. These three definition is defining what the omega, and which also can be calculated by 2 pi f. 2 pi f. F is the frequency of the alternating current multiplied by 2 pi is the angular speed or angular frequency. And calculating the maximum EMF is not so hard. Just you are going to write the equation BA and omega, and you will find what maximum EMF is. For example, a loop with an area of 0.33 meters squared A, rotating at 281 radian per second omega, with its axis rotation perpendicular to uniform magnetic field. The magnetic field has a strength B, 0.035. If the loop contains 37 turns of wire, and what is maximum potential difference? Calculate E maximum, which is BANO, BA and omega. You can find it very easily. And second one is also very easy. Just reverse is asked, EMF is given, B is asked. And then the structure of an AC generator. Yes, we induce an EMF by an AC generator, but what is the structure? How does it look like? We are going to now talk about this one. So a AC generator has four main components. One of them is, of course, magnet. If you don't have a magnetic field, you cannot induce an EMF. A permanent magnet provides a magnetic field, so N and S pole. And a conduction loop. So we need a loop or more than one loop, which is free to rotate in the magnetic field. So remember, we are going to change the orientation of the loop with respect to magnetic field and induce an EMF. Third one is two conducting rings called slip rings. One slip ring is this one, another one is that one. Each slip ring is attached to one end of the coil. So for example, this one is attached to left end, that one is attached to right end of the loop. And stationary graphite strips called brushes. Yeah, one brush is attached to one slip ring, other brush is attached to another spring, another slip ring. So as the loop is rotating, the slip rings are also rotating together with the loops. But brushes are stationary. They don't. They are always in contact with the rings, but they don't rotate. So brushes are used to get the electric current from the loop and give out to the lamp or the device which is outside. This is the basic structure of a alternating current generator. And as this loop is rotating, alternating current is changing according, look at here, so then it's sometimes zero, sometimes maximum, then zero, then negative value of maximum, zero and maximum. So now we will learn at what orientation of the loop it is maximum, at what orientation of the loop it is zero. So variation of EMF of a rotating loop of an AC generator. So when the loop is rotating, when the rotating loop is parallel, when it takes a position parallel to magnetic field lines, we will use an equation of induced EMF, E max sine theta. So here theta is the angle between the magnetic field lines and normal of the loop. Loop is horizontal, but normal is in vertical. So in this case, angle between normal and the magnetic field will be 90. Sine 90 is 1. For that reason, in maximum induced EMF is provided by the loop at this orientation. Yani when the rotating loop becomes parallel to magnetic field lines, so it provides maximum induced EMF. There is other methods to get this. So you are going to think the segments one by one. AD and BC segments are always parallel to magnetic field lines. If a wire is parallel to magnetic field lines, they don't cross it, and then they don't induce an EMF. But segment AB and segment DC, these two segments at this position are moving perpendicular. Segments, not the wire, not the loop. So as it is rotating counterclockwise, AB segment is moving down, down. CD segment is moving up, perpendicular to this magnetic field. So if a wire moves perpendicular to a magnetic field, it induces a maximum EMF. For that, as an AB segment and CD segment induces maximum EMF at this orientation. When the loop is parallel, a CD segment moves up, AB segment moves down, perpendicular to magnetic field, they induces maximum EMF. That's why induced EMF of the loop becomes maximum. But when the loop, of course, this loop will continue rotating, will take this position sometime later. When the loop becomes perpendicular to magnetic field lines, but normal becomes horizontal. So angle between normal line and the magnetic field is zero. Sine zero is zero, which means induced EMF at this orientation is zero. When the loop is perpendicular to the magnetic field lines, so at this orientation, induced EMF is zero, because all segments are moving parallel to magnetic fields in this orientation. Yes, loop is perpendicular, but segments are moving parallel to the magnetic field lines. And then zero EMF, zero EMF, zero EMF, zero EMF. No segment induce any EMF. That's why in net induced EMF of the loop becomes zero at this orientation. And alternating current is changing from zero to positive maximum, then zero, then negative value of maximum, zero, positive value of maximum. So then when the loop is perpendicular, induced EMF is zero. At what points loop is perpendicular? So induced EMF is zero, where A, C, E, G. So at these points, orientation of the loop is perpendicular to magnetic field lines. But when the loop is parallel, when rotating loop is parallel, it becomes parallel to the magnetic field lines. So induced EMF gets maximum value, which is B, D, F, H, or other these points. So induced EMF is maximum. So loop is at this orientation parallel to magnetic field lines. And this is all about. Then we will continue with the direct current generator, DC generators. This is the basic structure of an DC generator. But in AC generator and DC generator, three components are common components both in AC and DC generator. Permanent magnets, yes. Conducting loop, yes. Brushes, yes. But one component is different. In AC generator, we have two slip rings. Each ring is attached to one end. But in DC generator, we don't have two slip rings. We have single ring, but divided into two, which is called split slip ring, which is called commutator. And there are two segments, half segments. One half segment is attached to one end of the coil. Other half segment is attached to other end of the coil. And each brush is in contact with one segment. So this is the difference between the structure of a DC generator and an AC generator. We are going to change. All right, so this is the difference between the AC generator and DC generator. In AC generator, end of the loops are connected to the slip rings. There are two slip rings. But in DC generator, there is a split slip ring. We are going to split one slip ring into two. There are two segments, half segment. One half segment is attached to one end. Other half segment is attached to the other end of the loop. And this is split slip ring is known as commutator. So we can convert an AC generator to a DC by changing two slip rings into a commutator, or with a commutator. Okay, and this is the output EMF on AC generator. Yeah, if you use this generator two slip rings, output will be changing from positive to negative, from negative to positive, from positive to negative, from negative to positive, and so on. It is alternating current. But if we use a commutator instead of these two slip rings, one split slip ring, one commutator, we change this negative end to the positive. So this negative side becomes positive. So it becomes positive, 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 positive. This is one directional, always positive. This current is known as pulsating direct current. It's like a pulse. Zero maximum, zero maximum, zero maximum, zero maximum, and so on. Pulsating direct current. It's a direct current, but pulsating. So by means of commutator, pulsating direct current is provided to external circuit. So which component converts this AC of the loop to a DC in outside, which is the commutator. That commutator shifting this negative part from the loop to the positive. Commutator inverts negative part of AC current in the loop. Yes, in the loop still we have AC. Yani this loop still will have AC, but this commutator is giving it outside as a one directional pulsating current. Commutator inverts negative part of AC current in the loop as positive to external circuit. And of course, this is a pulsating direct current, but this current is not a perfect direct current. But it's bad. It is possible to get a steadier, much steadier direct current than this one. Only you should use more than one loop. For example, loop A is horizontal, loop B is vertical. When loop A is horizontal, it gets maximum EMF, so loop B is 0 EMF. Then it's rotating, loop B becomes maximum, loop A becomes 0. So when one of them is maximum, other one is 0. When one of them is 0, the other one is maximum. By this way, it is possible to get a steadier, much steadier EMF, much steadier direct current, which is less fluctuation, less wavy. So when we add these EMFs, we are going to get something like this. So it's going to be a little wavy, but better than this one. So by using more than one loop, a steadier direct current can be produced from a DC generator. And next device is the motor. Normally, motor is not the title of electromagnetic induction, because this motor is completely different than generator. In generator, you are rotating the loop inside a magnetic field and you get electrical current. So which means you convert mechanical energy to electrical energy. But motors are different. Motors, you are giving electrical energy, you are getting mechanical energy. So normally this title belongs to chapter 5, section 3, especially this part, how it rotates. Normally chapter 5, section 3, because you give electric current to the coil, like a galvanometer. Remember galvanometers? So galvanometer coil starts to rotate inside a magnetic field when you electric current is given. Motor is also like this. When you give electric current to the motor, so coils are starting to rotate inside a magnetic field. But their structures are the same. Maybe that's why they put it here. Motor structure and then DC generator structures are identical. So they have permanent magnets, yes. They have conducting loops, yes. They have commutators, yes, as you see to split slip ring, and brushes, yes. So only difference is motor converts electrical energy to mechanical energy, but generator converts mechanical energy to electrical energy, reverse. Yani you can use a motor as a generator, or you can use a generator as a motor. So it's possible. A motor converts electrical energy to a mechanical energy, which means you should supply some electrical energy by a battery. So a current is supplied to the loop of the motor by an external EMF source, which is a battery. This EMF source is a battery. And this current produces a magnetic field. So then, yes, when you give electric current to a loop, what happens? So this loop produces a magnetic field. We know it, chapter 5, section 2. Perpendicular to the plane of the page. A magnetic field of this loop will be perpendicular to the plane of the loop. So it will be vertical like this. There will be two magnetic fields in this case. One magnetic field is this permanent magnet will have a magnetic field in horizontal like this. And this magnetic field of the loop will be in vertical. And these two magnetic fields will start pushing each other, repelling each other. So fixed magnetic field of the permanent magnet and magnetic field of this loop start to repel each other, and this loop is free to rotate, then loop is starting to rotate inside this magnetic field. So fixed magnetic field of the permanent magnet and an S-pole repels the magnetic field of the loop, and loop starts rotating. And remember, I am going to remind you one title from chapter 5, section 2. When the plane of the loop is parallel to magnetic field lines like this is the loop parallel to magnetic field lines. So magnetic field of the loop must be perpendicular, but external magnetic field is parallel. So these magnetic fields cannot stay like this, because magnetic field lines normally, they don't want to intersect each other. They don't. But here, blue magnetic field lines which belongs to this loop and red magnetic field lines which belongs to the magnet, external magnet, they are intersecting each other. If you make this loop free, it will start rotating until this blue magnetic field becomes parallel and in the same direction of this external magnetic field. So when the loop is parallel to the magnetic field lines, it starts rotating until this loop becomes perpendicular to magnetic field lines. So their magnetic fields will be in the same direction. This is how a motor rotates. So we are making the magnetic fields perpendicular to each other, and then you keep release this loop free to rotate, and this tends to rotate until it becomes perpendicular to external magnetic field. So both magnetic fields becomes parallel. So a fixed magnetic field, you pass the loop's magnetic field, so the loop starts to rotate. Rotation continues until both magnetic field becomes in the same direction. So fixed magnetic field and loop's magnetic field are parallel, so the loop does not tend to rotate at this position and rotation stops. But we want motor to continue rotation. How can we do that? So then if you change electric current direction in this loop, and if you change the electric magnetic field of the loop, so this fixed magnetic field will continue pushing the repelling the loop's magnetic field. At this location, when the loop is perpendicular to external magnetic field, commutator alternates electric current direction in the loop, so magnetic field direction becomes opposite. It becomes to the left. Then fixed magnetic field continues pushing the loop's magnetic field, and loop continuously rotate inside this magnetic field. So then which device or which component of a motor provides continuous rotation of a loop, which is commutator. Commutator alternates electric current direction again. So it makes direction, it alternates, it changes direction of the electric current on the loop. So sometimes clockwise, sometimes counterclockwise, clockwise, counterclockwise, and then continuously shifting this magnetic field, blue magnetic field, and causing the fixed magnetic field to repel this magnetic field of the loop. And this is a movie about how motors are running. Just briefly, I will explain on this. So uh, this motor has, as I said, a coil, and each coil has two ends, and each end is attached to one slip ring. Has one segment of the commutator. One segment is attached to right end, other segment is attached to left end, and the coil is located between the external magnetic field. And brushes, of course, these two are brushes are attached to the each segment of the motor. The stator provides a constant magnetic field, and the armature. And these magnets are providing the constant magnetic field, so it's from N to S. Which is the rotating part, is a simple coil. The armature is connected to a DC power source. And of course, you need a DC power source. It's a battery. So battery's positive terminal must be connected to one brush. Negative terminal must be connected to other brush. Of course, this provides a current. So current will start from positive, will continue through the coil, and then leave from negative. So electric current on the coil will circulate according to this picture, clockwise direction like this. So then when electric currents are flowing in the coil, this, as I explained, according to right-hand rule, for example, if you look at the direction of the magnetic field of the coil, it will be down, which is perpendicular to the external magnetic field. So then this loop will start rotating. According to the Lorentz law, so the coil will start to rotate. It starts rotating. Sorry, let me get back again. Yes, it will start rotating, and then where at this position, now magnetic field of the loop and magnetic field of the external magnetic field becomes in the same direction. So then normally at this position, motor must stop. But here you see that this this brush is initially in contact with this side, but later it will get in contact with the blue side, which means commutator will change the electric to current direction on the loop. As electric current direction changes, so then magnetic field direction also changes, and then force direction also changes. So then this coil continuously rotates inside the magnetic field.
This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero.
So here is normally there is no rotation, but direction of the electric current is changed, and then it provides continuous rotation again. But rotation is not so regular here. It is irregular rotation. To provide a regular rotation, you have to provide one more loop. Yeah, in this case, rotation becomes regular.
In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system.
So this is much regular rotation than the only single loop, more than one loop.
Moreover, the more such loops.
Normally, this is the structure of a motor. There are so many coils, all they are located like this, and then they provide the rotation to be much better. Okay, anyway, so this is how a motor rotates, and then next step is, of course, to get back EMF as motor rotates in fixed magnetic field of the bar magnet, permanent magnet. Of course, if a loop rotates inside a magnetic field, magnetic flux through the coil also changes. If there's a change in magnetic flux and induced EMF and EMF is induced in the loop, yani motor, yes, we are providing some electrical energy to a motor and then causing to rotate inside a magnetic field. But as it is rotating, this motor also acts as if a generator. It also induces an EMF. This induced EMF right now for motor is called back EMF. In fact, this back EMF, the same as induced EMF in generator. Equations are the same, change is the same, it's alternating EMF. But it's called back EMF because it acts to reduce the electric current in the coil. So this is the motor. You are supplying this motor to some external EMF with positive and negative terminal, but motor itself also behaves like a source of EMF with positive terminal and negative terminal. And in this case, because these two EMFs are opposite in direction, net EMF or potential difference supplied to the motor V becomes less than E because this is opposite polarization. This back EMF is opposite polarization of EMF of the battery. So potential difference supplied to the motor V equals the difference between applied potential difference of the battery and back EMF of the motor. Yani V supplied to the motor is E minus C back. E is constant because it is just belongs to the battery, but E back can change. E back can change according to the Bernoulli equation. As I said, back EMF is no different than the induced EMF. It's a kind of generator. B, A, and omega is the equation for back EMF. If omega increases, yani if motor starts rotates faster, omega increases, back EMF also increases. Yani if somehow motor is starting faster and faster and faster, back EMF is also increasing. If back EMF increases, because battery's EMF is constant, it is 1.5 volt, for example, if back EMF increases, so then potential difference supplied to the motor must decrease. So potential difference supplied to the motor decreases according to Ohm's law. If this V is decreasing, because resistance of the motor is constant, I must decrease. So here, this part is very important because there are some questions asked about this part. Okay, if motor starts rotating faster, If omega increases, back EMF increases. If back EMF increases, V decreases. If V decreases, electric current supplied to the motor also decreases. This is what back EMF is and how back EMF changes for a motor. And the last title in this section is about the mutual inductance. So mutual inductance, in fact, the basic of transformers we will study in chapter 6, section 3. It is the first electromagnetic induction experiment done by Michael Faraday. So there are an iron ring, and around this iron ring we wrapped two coils. One coil is called primary coil attached to a DC battery. Other coil is called as secondary coil connected to a galvanometer, zero-centered galvanometer. So when switch is open, so then there is nothing. There is no current. There is no magnetic field. There is no magnetic flux. So galvanometer reads zero. But when switch of the primary circuit is closed, when you make this closed, you provide a current to this primary coil. If you provide a current on primary coil, which means you produce a magnetic field in this coil. This magnetic field circulates on this iron core like this and causes an increase in the magnetic flux for the secondary coil. Yani initially magnetic flux was zero when it is open. When make it closed, magnetic flux in the secondary coil increases. And this increasing magnetic flux in the secondary coil induces an EMF on the coil, and this galvanometer deflects in one direction. Say that when you made it close, it deflects to the right. But as switch of the primary circuit is kept closed, if you keep it closed for a long time, so then current on the primary coil becomes constant. If current is constant, magnetic field produced by the primary coil is constant. If magnetic field is constant, magnetic flux through the secondary coil is constant. If magnetic flux is constant, which means there is no change in magnetic flux, there is no induced current. That's why galvanometer reads zero. But when the switch of the primary circuit is opened, when you make it open, initially it was closed and opened. As soon as you make it open, current in the primary coil decreases. Magnetic field of the primary coil decreases. Magnetic flux on the secondary coil decreases. So if magnetic flux in secondary coil decreases, a current is induced in the secondary coil, but in the opposite direction. That's why galvanometer deflects opposite. If initially when you make the switch on, when you make the switch closed, if galvanometer deflects to the positive, when we make the switch opened, galvanometer deflects to the negative. Their directions of deflection will be opposite. This is mutual inductance. So by changing the electric current on one of the coil, you induce electric current EMF on the secondary coil, which is known as mutual inductance. And mutual inductance equation is no different than the normal self-induction equation. So we change the electric current, delta I over delta T, and multiply by coefficient of mutual inductance. You are going to get equation E. But here, we are changing the electric current in the primary coil. We get induced EMF from secondary coil. In self-induction, it was not like this. We were changing the electric current in the primary coil. Normally, there was no primary coil, just one coil. You get EMF from the first coil. But here, two coils exist. One of them is primary, the other one is secondary. And the magnetic flux through the secondary coil changes. Yes, magnetic flux through the secondary coil here is changes. And induces an EMF in that coil as current in the primary coil changes by time. So we got induced EMF from secondary, so by changing the electric current in the primary. So delta I over delta T, this change belongs to the primary coil, induced EMF belongs to secondary coil. And M is called mutual inductance constant. It's a constant number. Its unit is again Henry, the same as the self-induction. It depends on two things. One of them is specification, length, number of turns, or of two coil system, or area, or the medium. But second thing is orientation of two coils with respect to one another. So mutual inductance is maximum when the coils are parallel to each other, and mutual inductance becomes minimum when coils are perpendicular to each other. So this is the end of this section 2 which is about the uh,